So Mr. Crothers made a publication here, Time Warps and the M87 Black Hole. Of course, I agree with Mr. Crothers. The black hole idea is more like a zombie theory. It's dead, but it still walks around, you know? But he has some ideas in here of why the black hole doesn't exist. And I have my own ideas. And quite frankly, I think my ideas are the easiest to understand. Stars can't become black holes. It's as simple as that. When they cool and collapse, they combine their elements into molecules and molecular compounds and form things that are called rocks and minerals. As stars evolve, they become giant rocky structures that we call planets and exoplanets and gas giants. Of course, the gas giant is an intermediate step, and that loses its thick atmosphere, and eventually the rocky differentiated core is left over. But the stars, they're physical. They're not mathematical. You can actually see them. You can actually experiment with them. You can take measurements of their spectrums. What is the spectrum of a black hole? It doesn't have a spectrum. It doesn't have anything worth studying. The fact that it looks like a donut is like, come on, man. I don't. Dead stars are giant rocks. It's as simple as that. That's what rocks are. They're the remains of a giant star that's evolved over many, many billions of years, and it's combined all its elements on the periodic table into what we're familiar with, what we can cliff dive off of, what we can throw at each other when we're angry. But this paper, Oxygen, I have here. Let's go and read the abstract for you. For this paper, the term primordial oxygen is used to signify oxygen that has been present for almost the entirety of the star's evolution. The case stands. The oxygen found on the Earth is leftover oxygen from the Earth's much hotter, younger states of evolution. The vast majority of the oxygen on the Earth did not come from the sun. It was always on the Earth as it evolved long before the sun even existed. All the elements are important for planetary evolution, and oxygen is a major one. I don't want to read this whole paper out, but basically we have a realization from the Genesis spacecraft that came back. There's a picture of Genesis. That spacecraft took measurements of the solar wind coming out of the sun. It captured the particles coming out of the sun. And long story short, what they determined is that this is from Kevin McKeegan at UCLA. The implication is that we did not form out of the same solar nebula materials that created the sun. Just how and why remains to be discovered. And I have here, it's not only an implication, but it is expected and normal. Why? Because the Earth is its own independent star, vastly older than the sun. How? The sun adopted the Earth far into the Earth's own evolutionary history, or evolutionary past. It is much younger than the Earth, about 100 times younger. The Earth isn't just some giant rock that clumped together from much smaller space rocks, pebbles, and gas. It is the core remains of a many billion-year-old star that has gone through vast amounts of chemical evolution, dissipation, and differentiation. Okay, and here's some chemistry for you guys. As the sun gravitationally collapses, heads into its next cooler, less massive, and less radiant stages of evolution, it's going to become an orange dwarf. It will lose large amounts of its oxygen, but a lot will remain. That oxygen far into its future will get covalently bonded to the hydrogen in the atmosphere, forming water and various other compounds. We call those compounds minerals and rocks, and are essentially settled out of a solution. So there's a little bit of Neptunism there that's actually correct, the Neptunism of the 1800s. In fact, since oxygen has a high electronegativity of 3.5, only beat out by fluorine. Electronegativity means it pulls in electrons the strongest. So it's very, very, very reactive. It's chemically reactive. Only beat out by fluorine, and is the third largest component of young stars like the Sun. We can guarantee a very large portion of dead stars will be composed of oxygen. The oxygen as a free radical will grab anything it can get its outer shell full, so it can get its outer shell full of electrons. This is a fact of chemistry. It is true even if there are very little surface volatiles, meaning no atmosphere, which are compounds that boil away easily. Volatiles meaning if you heat up something, it's just going to vaporize into gas. It's not going to be very easy to handle because it has such a low boiling point. Earlier during the star's evolution, it had its gravitational potential energy from gravitational collapse transform into heat energy. And that's the big difference between stellar evolution forming planets and stellar evolution forming black holes, is that when you have something gravitationally collapse, that gravitational collapse energy, the gravitational potential energy, is transformed into heat energy. And that heat energy is used to fuel chemical reactions on vast scales. That heat energy in the interior of cooling stars then could facilitate the reaction of oxygen with literally all naturally occurring elements in the periodic table, some more than others. This is why there's so much oxygen in the rocks and minerals. And this is why oxygen is found binded to almost every single element. It's because it's very reactive. And inside the star, it had all that room to mix. We can see direct observational evidence, even in the sand on the beach, which is silicon dioxide, which is SiO2, 1 silicon and 2 oxygens, and granite and even basalt, which composes the ocean floor. Dead stars like Mercury should have lots of oxygen in its rocks and minerals, trapped in crystalline form, meaning its volatile material is there, only combined in much more stable molecular compounds that are hard-pressed to vaporize. And that's a very important point. When you have oxygen as just a gas, which is a diatomic molecule, you have 2 oxygen atoms bonded together. That is a volatile by itself. It vaporizes easy. You breathe it in. You exhale it when it combines with carbon as CO2. But if you take that oxygen and you combine it with things like silicon, you make sand. When you combine it with things like titanium, you make titanium dioxide. And titanium dioxide is material they find on the surface of the moon. And titanium dioxide is also found inside of red dwarf atmospheres as they cool, shrink, and evolve. So titanium dioxide is literally one of the first strong chemical compounds that's made inside of a star. Middle-aged stars such as Jupiter and Saturn should also have lots of oxygen in their interiors as they are cooling and differentiating their interiors. Neptune and Uranus, which are even further along in their evolution, should have an even higher ratio of oxygen in their interiors than Jupiter and Saturn. Now, I said ratio of oxygen. It doesn't mean they have more oxygen, it's just their ratio is considerably less. So, even if they have, like, say, 100 pounds of oxygen, Jupiter has 100 pounds of oxygen, Neptune will have maybe 15 pounds of oxygen. But the oxygen that Jupiter had versus the hydrogen it had is a lot lower. So there's way more, there's like 10,000 pounds of hydrogen. But then with Neptune, it would be maybe about 100 pounds. So it's like a sixth versus 1/100th or whatever. Here. Neptune and Uranus, which are even further along in their evolution, should have an even higher ratio of oxygen in their interiors than Jupiter and Saturn. They are moving into ocean world stages of evolution, so they're going to be covered in deep water oceans. The huge diversity of oxygen containing compounds that exist on the Earth and other highly evolved stars can only be explained via stellar metamorphosis. Yada, 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 yada. Okay. The researchers who claim that dust and gas just clumps together in outer space to form planets have to answer this question. Can the vast diversity of elements be combined chemically and in huge amounts in the vacuum of outer space to make minerals and rocks? The answer is no. You absolutely need a flask of stellar proportions to make such diverse chemical compounds, and in quantities present in the interior of the Earth. As well, you need a forming surface so that the material can settle out, deposit on the giant planetary substrate in the interior of the star, and give direction for the settling, the gravity. Basically, the thick atmospheres of evolving stars, as they cool, act as both a type of solute and solvent, depending on what type of reaction you're recording. All in all, there are around 3,695 valid species containing essential oxygen listed below. So here's how diverse the oxygen is when it combines inside the interior of the star. You have one valid mineral species as the element, sulfides, sulfur salts. You have halides, oxides, carbonates, borates, sulfates, phosphates, arsenates, vanidates. That's probably vanadium in there. Silicates, and organic compounds. Organic compounds. Now, organic compounds, well, with oxygen, with biological, once you add the carbon in there, holy crap. Probably hundreds of thousands of different chemical combinations with amino acids and that kind of stuff. But anyways, black holes don't exist. Stars become giant rocks. You get it. Later, y'all.